we present OpenBot-Fleet, an open-source system for collective learning with real robots. This supplementary video provides a quick introduction to our paper and results. Recent developments in cloud robotics highlight the benefits of connecting large fleets of robots to vast computational resources to support iterative learning from real-world interactions. Despite these achievements, only large technology companies currently have the resources to operate the vast fleets of robots needed to acquire, often private, datasets, or to implement the robot policy improvement loop at scale. In this work, we introduce OpenBot-Fleet, an open-source, yet comprehensive solution to this challenge, showcasing a cloud robotics system specifically designed for wheeled robot navigation. OpenBot-Fleet harnesses the power of smartphones mounted on robust yet low-cost open-source wheeled robot platforms for sensing, local computing, and communication, while synergizing with Google Firebase for secure cloud storage and computation. Modern smartphones are powerful multi-core computers with a comprehensive sensor suite and abundant communication interfaces. OpenBot vehicles are open-source, inexpensive, and easy to build. Each vehicle contains a sonar for distance measuring, bumpers for collision detection, and encoders for tracking movements. All this, powered by a battery providing several hours of autonomy. While engaging with their environments, robots collect substantial volumes of diverse, task-related data. Once transmitted to cloud infrastructures, this data can be harnessed to fine-tune and enhance operational policies, which are subsequently relayed back to the robotic cohort. The framework seamlessly integrates an imitation learning pipeline as well as a reinforcement learning pipeline, leveraging data collected from a fleet of robots operating in real or simulated environments. Simulation environments are typically used for optional pre-training or policy evaluation purposes. We currently support Unity and Intel Spear as the main simulation platforms. For real-world deployments, we provide an Android app that allows crowdworkers to control a robot using their own smartphones. Beyond fundamental perception and control tasks such as policy inference, this app encompasses higher-level functionality such as authentication and communication with the cloud, ensuring consistent synchronization and deployment of up-to-date control policies across the entire robot fleet. We here present a typical round of distributed reinforcement learning in the context of a point-goal navigation task. Each crowdworker has to manually drive his robot towards a self-defined goal while avoiding obstacles along the way. Using the latest control policy, automatically downloaded by the app from the cloud, the robot will then try to return to its starting point, while recording its actions, observations, and any potential failure modes occurring along the way, such as collisions with the environment. Once the episode is over, the user is invited to check the recorded data, then upload it to the server so that it can be used in the main reinforcement learning loop. The process then repeats with a new recording. We validate the different components of our system, namely the simulation pipeline, imitation learning pipeline, reinforcement learning pipeline, cloud backend, and scalable learning and data collection pipeline by training a distributed indoor point-goal navigation policy. Our navigation policy leverages a self-supervised perception backbone, trained with the data collected by distributed workers in 72 distinct indoor environments. The perception backbone is a U-net which learns to segment the floor and extract the floor boundary as a representation for the controller. The ground truth is obtained using a gradient threshold on the depth generated by Midas and further refined using GrabCut. More details can be found in the supplement. The controller is a residual network with respect to a unicycle model. It is first pre-trained via reinforcement learning within a Unity simulation where it has access to privileged information. We then fine-tune this control policy in 4 distinct real environments using our reinforcement learning pipeline connected to the cloud backend. The results suggest that our method delivers superior performance compared to the baselines with success rates of at least 80%, ranging up to 90% in all 4 test environments with fewer than 200 fine-tuning episodes. Even without fine-tuning, our model achieves zero-shot success rates of at least 50% in unseen environments. Ablation studies executed on the perception backbone show a clear correlation between the evaluation metrics of the perception backbone and the zero-shot success rate of the experiments. A clear trend emerges. As the diversity and quantity of data increases, the performance metrics, and hence the overall system performance, also tend to improve. Thanks for watching. You will find more details in our paper and supplementary document.